than maximum static friction?
Sorry, Christopher. I put the recording on and it blocked out what you were
Okay.
asking me. So if an object is stationary,
Yeah.
well,
And we want it to begin moving, will the
mhm,
force applied need to be greater than the maximum static friction?
yes,
Okay, so it can't be equal, right? Because if it's equal, it wouldn't still move.
it would not move. It's
Okay,
over that
okay.
it will move. Yes.
And then in chapter 12, additional problem number 7, um, I was just wondering if the answer was had the wrong sign.
12, additional problem number 7. The ball thrown with initial, what is the velocity if it is caught?
Yes. Yeah.
Um,
Can it be negative since it's going down? Because we're talking about velocity in this case.
you are technically correct.
Like assuming we're throwing it up in the beginning. I guess you.
Technically, what you would be putting there is it would be 20 meters per second at an angle of 35 degrees
Yeah.
down with respect to the horizontal, right?
Okay. Yeah.
Um, so it's not a negative because the angle is not perfectly up and down, right? We are
Okay.
not we're not doing straight up, straight down. We are doing it at an angle of 30 degrees to the horizontal here, so it would be 30 degrees to the horizontal here, and you kind of have to show that. Makes
Okay.
sense.
So for the midterm, like what are we expected to know for levers? Like examples or just because like the calculations was just mechanical advantage. I'm not too sure what else.
There's two things, mechanical advantage
Yeah.
and balancing torques, really. Um,
Okay.
we did some examples where if you're on a first class lever and you've got a 20 kilogram child on one side and a 40 kilogram child on one side, and the 20 kilogram child is, um, I don't know, a meter from the axis. How far away does the other child have to be? That kind of thing.
Okay. Just so basically setting the torques equal to one another and solving for the variable.
Yeah.
Okay.
Mhm.
And in this midterm, it's free navigation, right? Like the first midterm.
Yeah, it will be free navigation.
Okay. And no uploading, none of that stuff.
No uploading, but there will be some questions that we will actually have to mark that
Oh,
are,
yeah.
where you might have to type in a solution or a description of the answer.
Okay. Because I was just wondering for free body diagrams, it's kind of hard to,
Yeah,
draw them
free
out.
body diagrams. I know you're not going to. The answer to that is clearly you're not going to have to draw a free body diagram and upload it. No.
Okay, perfect. Thank you.
Well, it's perfect, but I wish I could. It's interesting because last year at that doesn't mean you don't need to know free body diagrams. I'll
Yeah,
get
for
at
sure.
it
Yeah.
another way.
Yeah.
Um, this is how I know when we went into lockdown last year. The second midterm was done on paper. Last,
Online?
no, it was done on paper last year.
Oh, okay. In person, I see.
We just got it in person, and then the lockdown came that week, was announced that weekend.
Oh, okay, yeah.
So we just got that midterm in before the lockdown. But anyway, yes,
Okay, thank you, Dr. Moore.
you're welcome. Um, what I said was that if you have a free body diagram, you won't have to draw them because I'm not going to have you upload them. Okay. Let's just see where we are. I think Manver, you're next.
I had a couple questions.
Mhm.
So for the first one was the midterm. Like, when you say it's cumulative, so are there going to be questions like directly from radial acceleration velocity and all that?
Could be. Look at it this way. This is my perception, and I won't give you a percentage and all those things. And yes, it might be a little bit more on the stuff on the second half, but I'm not going to give you a number because we did force equals mass times acceleration in the second half, or in the second third, excuse me. And that means you have to calculate an acceleration. And you need to understand velocity and acceleration. And it's a course that builds on itself so much that, we did all that vector analysis piece. That was all from the first term. And yet you use it in almost every one of these problems, right? So for me to say the only thing I won't put in, and I've let you know that, is a projectile analysis question.
Okay. And then also, could you go over one question? It's on page 418. It's question 4.
418, number 4, the hand on the scale.
Yeah. And
that actually is not on the midterm.
Yeah, I was just gonna ask that. So like questions like question number 4 and 3, those won't be on it, correct? Because they're like static?
Because they are static equilibrium, and that was on this week's lectures. I mean, they were posted last week, but they're this week's lectures. So I will not have the joint level or whole body level static equilibrium on this exam or on the test, okay? Do you want me to still go over it, or do you want to wait until next week?
Could you still go over it? Because I already did those questions, and that was the only one I couldn't get the answer for.
Okay, well, I don't mind going over it. I'll go over it quickly because I'm sure there's other tests. Let me, actually cancel that. I have to bring up my whiteboard because with this one, the whiteboard does not show up as an option. Okay, so this is chapter 12. For those who, chapter 12, additional problem 4. The key thing is to get a good free body diagram. And again, I'm doing this relatively quickly because this is not, so we have the forearm, because we have to cut through the elbow. In order to figure out what's going on at the elbow, we need to do it. The elbow is not at the end in this one. It's basically there because the triceps actually pulls in there on the other side of the elbow, and the biceps is on this side of the elbow. Sorry, straight up. In both cases, they're going at we happen to be in a posture here where these are going at 90 degrees, and they tell you that. There is a weight here, and there is a force under the hand which is pushing up. They tell you how much force is in the biceps. I know that people had problems last week hearing it. I'm going to just try and be a little bit somewhere in between. So they give you that as being 3 centimeters. They don't give you any information about the biceps because the biceps is the antagonist muscle in this case. So we're going to assume that it's not on. We know that this distance is 17 centimeters. We know that this, the The weight of this is, the force due to gravity is going to be 40 newtons. And we know that the force on the scale is 90 newtons. And that distance is 32 centimeters. So the sum of the, there's our this, and let me just get rid of the biceps because, hey, they aren't in this one. Sum of the torques around the elbow equals 0. And we also have our reference frame, so we figure out which way's 0. So anything that tries to rotate around, again, hold your pencil, put it over top of what you're looking at, and anything that pushes up and makes it rotate counterclockwise, I'm going to call it positive. Anything that causes it to rotate clockwise is negative. And note that when I push up on my triceps, it's going to rotate it around in a clockwise or negative situation. So this is going to equal 90 newtons times 0.32 meters minus 40 newtons times 0.17 meters minus the force in the triceps. That's supposed to be that, just if you're wondering, that's an S scale. Force in the triceps times 0.03. .03 meters, and that all equals 0. And then when you now rearrange and solve for the force of the triceps, is going to equal 90 times 0.32 minus, minus 40 times 0.17, all divided by 0.03, which I think will equal the 733. Fair enough? Any questions on that?
No, that's good. Thank you.
Okay, good.
Just a quick question.
Yeah.
So just to confirm, like this type of question won't be on the midterm?
It is not going to be on the midterm. No,
Okay.
it's, I mean, it was this week's lectures.
Oh,
And
okay.
so is there some sort of lever balancing type questions? Yes, but this full equilibrium of a whole body or a joint will be on the final.
Okay, cool. Thank you.
Okay. No other questions on this one? Okay, we'll stop sharing. I think next on the having their hands up is Danny.
Good morning, Professor.
Hi.
I had one question from chapter 13, the application problems, and two quick ones from the introductory problems, both on chapter 13.
Okay.
So my first question, chapter 13, application problem, additional problem number 10.
Okay. I won't go through all of 10 now. I will show you the parts of 10 that you would need to know for this course. I love question 10. I have fun doing question 10. We all have, different things we have fun with. I enjoy doing a challenging math type question. Let's share our whiteboard. So with 10, the part that you would need to know is the part, and this one again is, it's just on the edge of understanding that the sum of forces, it's on the edge of equilibrium. But basically you have a you have a patella, you have a tendon force A tendon force A really being the quadriceps, B being the patellar tendon, TB, and F. And really, this is a sum of the forces in the X direction equals 0, and the sum of the forces in the Y direction equals 0. Again, equilibrium, so we aren't really going to, it's not going to be of the same nature in this, on the midterm. But what you do in this question, and I'm just going to leave with what you would do in this question for now, and I will happily do the whole thing next week, is you're going to, and this part is something that you should be able to do at this point based on what we've learned. Actually, it's from the first third of the course, and you have to break each of these forces into their components. And of course, this is a free body diagram, so we are going to have our reference frame. And when you do this, so let's say the sum of the forces in the X direction, you are going to, after you've, and you're going to have your sines and coses of this, of each of these to figure out, because of, let's see, this guy's 38, this one's 29, and this one is 30 in here. And you know that this guy is 80. Knowing that that one's 80, and just knowing that the sine of 30 is half, this is going to be 40 newtons. And this is going to be 80 times cos 30. I think you get the idea. This one's going to be F cos 29. And this guy is going to be TA cos 38. And these guys are going to be your sine ones. So this would be, for example, TA sine 38. So the point is here that you are going to get all of your X's and put, like, at this is where you should be able to get to without the equilibrium, is to recognize that there are all these components. And I mean, this is at this point, it's really not any different than the 3 kids pushing on the post in chapter 3. because you are literally adding up your three forces, your TB plus your F plus your TA. And in doing that, you're going to have your X components, which are, for example, sorry. And you're going to have your Y components, which are okay. That's where I'm going to leave it for today, because that's really all you need to know for now. I hope that helps. What you're going to get in order to solve this, and this is where it becomes tricky, and I would never ask you this kind of question on a test, because it's not a test of your understanding of biomechanics once you get to this point. But it's a test of your understanding of solving mathematical problems, because what you end up getting is two unknowns and two equations. Your two equations are this guy and this guy, and your two unknowns are your fx. Well, your two unknowns are F and TA. And so by substituting into your Fx, you're going to get your F cos 29, for example. And here you're going to get your F sine 29. And TA, you're going to have your TA cos 38. And here you're going to have your TA sine 38. And so you've got two unknowns, F and TA, and two equations, your FX's, your forces in the X direction, and your forces in the Y direction. And this Fy is not the same as this Fy, by the way. This is all of the forces in the Y direction. This is specifically the component of this force F in the Y direction. And you actually have to rearrange it and substitute. So you solve it for example, TA, and then you have to take that and substitute it in. At that point, it becomes a math issue, and it's fun to do if you like math problems, but it's not necessarily a biomechanics problem at that point. Any questions on that?
Thank you, that helped.
Okay, good.
So for introductory problems, I just had two quick questions.
Okay.
It was number 7 and number 10. Number 7, I just wanted to make sure that my reasoning was right, since like no answer is provided. And for number 10, I was just wondering like how you would do that one, because I used the equation that you showed us in class, and like I plugged in everything properly, and I didn't get the answer that the book gives.
Okay, well, question 7 is that the mechanical advantage of a first-class lever can be greater than, less than, and equal to 1. It can be all three. It just depends on how it's set up. So think of a teeter-totter and what would require it to balance. And you have two kids, and in one case, the heavier child is the applied force, and the lighter child, this would be equivalent to the adult being the applied force and the child being the
Resistance?
the load. Yeah, the resistance force / load. And typically in that situation, you would have the lighter child, the child out at the end, and the adult would be really close to the actual pivot. So if you put the loads over the moment arms, which is the distance from the pivot to the adult, over top of the distance from the pivot to the child, that's going to be less than 1. Okay, so that would be a case where it is less than 1. If you rearranged it and said the child is the applied force and the adult is the resistance, then you would have a large number, the distance from the pivot to out to the end where the child is, over top of the distance from where the pivot is to where the adult is, which is smaller, so it'd be greater than 1. That would, and a good example of that would be if you're trying to pry a rock or something like that, where the load, when you pry a rock or use a pry bar, you always make it so that the distance from whatever you're using to pivot it on to where the rock is, to where the load is smaller than the distance from where you're pivoting it to where your hands are, so that you don't have to exert as much force. That gives you a mechanical advantage greater than 1. You have 2 equal size, equal weight children on the teeter-totter. They're both going to sit in the seats equal distance away. That will be a mechanical advantage of 1. That help?
For sure, that helps a lot. Thank you.
And 10, I did do 10 last week, but we can just very quickly about it. First of all, the thing with 10, compared to what it shows in the book, is to think of this as being zeroed. The same way, if you have a kitchen scale, you would put if you have a kitchen scale, you would have well, let me just show you. And you wanted to know how much you had to do something by weight, and you're going to put it into a bowl. You would put the bowl on first, and then you would zero that scale so that it doesn't include the weight of the bowl, right? And then you would put whatever it is that you were going to put in the bowl that you were doing by weight. Let's say butter by weight. And so that everything that was being shown on the actual scale was only the weight of the butter, and it didn't include the weight of the scale. You would do the same thing, or the bowl, excuse me. You would do the same thing here with the reaction board. You would zero it with the board on it, so you don't have to take into account the weight of the board.
Would we be expected to make these kinds of assumptions for the midterm, or will you be explicit as to
what? Well, in this particular case, you might actually figure it out all on your own, but I would probably say, something to the effect of the weight of the board is not included in the scale measurement. Okay. So what would happen is basically you have a pivot here, and you have the scale here. And so there's gonna, and you have the weight of the person here. You know that this distance is 2.5 meters. You know that this is 400 newtons. And you know that this is 600 newtons. And this is the distance of the center of gravity of the person from the platform support, which is also the pivot. So now you've got 2.5 times 400 newtons on one side, and that's going to equal D times 600 newtons on the other side. So now you can solve for D. And newtons will cancel. You'll be left with meters. It'll be 2/3 of 2.5 meters, which is the 1.67 meters. Fair enough? Any questions on that?
I have a question. So if they had given us the weight of the board, we would have to put that into consideration when we're calculating, or do we have to just make the assumption that we can use it?
The weight of the body?
Of the board. Like there is some formula I saw that D where like you multiply everything and then you subtract. Like there is a long formula in the textbook that they gave to find D, including the weight of the board.
Yes, exactly. I totally agree. And if I gave you the weight of the board and I told you the scale included the weight of the board, then you would have to use that equation.
Okay.
But what you can do in this type of scale is zero it with the weight of the board on it. So you adjust this scale here so that it is zero with their when the board is when the board is on it and the person isn't. So then you've taken away the effect of the board. And that's what they're doing. And that's why I use that analogy of the kitchen scale that you can adjust to zero. You zero it out. There's a lot of scales that you zero out before you actually do the movement so that you know that what you're measuring is only associated with what you're looking at. Okay, any other questions on this one? And yes, they don't tell, after giving you the full long equation in the textbook, they don't tell you that it's zeroed out in this one.
Thank you.
Okay. Aaliyah, I think you're next. Or Ellie, sorry. No, Aaliyah. Aaliyah.
Hi, Dr. Yep. Hi, Dr. Moore. How are you?
I'm good. How are you?
Good, thank you. I had a few quick questions. So the first one from lecture 13 about 12 about the free body diagrams. Can you show how you would determine for, let's say, like free rotation around a joint, like for a pin joint, can you show how you would determine the horizontal and the vertical components? Because for some examples, like for the biceps, for example, sometimes the vertical would be pointing down and sometimes it would be pointing up. So I just wanted to know how you would determine that.
Okay, well, a very good question. Share. Okay. The key thing to know here is that you don't know. You don't know ahead of time. You just don't know. So it could be either way. It depends on all of the forces that are acting on something. You can't look necessarily, I mean, with experience, you would kind of get, so you might know, but you don't necessarily know ahead of time what direction the forces in the joint are. And it's literally the forces that are going to hold the joint together. And if you have, so you have a free body diagram. Let's use the classic forearm biceps one. And there's, you know, maybe some gravity associated with this. There might be a force in your hands, and your force in your hands could be any direction. It could be that direction. It could be that direction. It could be that direction. You don't know what direction. If somebody's pushing on your hands, it's going to be like that. If somebody's pulling on your hands, it's going to be this direction. So you don't always know which direction that's going to be. You have your elbow, you have your triceps acting in whichever direction they are acting, and that depends on the posture of your arm. And the same thing with your biceps. It could be acting in whichever direction. And again, whichever is the agonist muscle, biceps or triceps, depends on what's happening over here. So the point is, there's a lot of different forces that can be acting on that arm, that both internal, the muscles, and external, the gravity, and then whatever force is on your hand, and put together. It's not until you add them all up that you find out what's going to actually be happening at the joint. So let's say I have a situation where somebody's pulling on my hand. Still got gravity here, and hard to say whether it's going to be biceps or triceps. Let's just put a muscle going there. And then you have joint reaction forces here. I can draw them. I normally draw an X and a Y component, and I normally draw the X and the Y component in whichever way I want to. It is up to you. That's why you draw it in there. But you have to understand what it means. So if a force is acting this way onto the elbow bone, that means it's pushing into the ulna, right? You've got the humerus and the ulna, and if it's acting that way, it's pushing in into the ulna, and that it's pushing up on the head of the ulna. It may or may not be doing it that way. It might, you know, in this particular case, depending how big this is, it could actually be going the other direction, but you don't know. You honestly don't know. There's a component of this muscle force, assuming it is the biceps that are active. And again, that you don't know that unless you've done all the checking out what's going on. There's a component of this muscle force that's acting this way, and it might be big enough that it counteracts this force. You don't know. Point being, you can draw your joint forces components, your X and Y joint force components, in whichever direction you want, as long as you solve for it, knowing what that means. And if you get a negative for either one of these components, it just means, so if I solved for all of this and I got a negative 50 newtons here for my y component at the joint, it means that the y component of the joint force is acting down. I don't really change my free body diagram because as I go through motions, I sometimes it might be negative, sometimes it might be positive. So all I do is I say 50 newtons acting in this direction, which means it's actually acting down. Does that help?
Yes, thank you.
You're welcome. And I also would say too that if I don't know exactly which force is acting, because as I said, depending on things, this could be a biceps or it could be a triceps activity, I can do the constrained version of this, which means I just say that this is a torque created by the muscles. As I've drawn it, it would be the biceps because it's going to try and raise my forearm in a flexing type of direction. And I would solve for this torque first before I solved for these guys. In that case, I actually will not have the exact same numbers for these guys. The X and Y component of my joint forces kind of underestimates what that actual bone-on-bone force is, but it does allow us to solve the problem without knowing whether it's the biceps or triceps that are active.
Okay, that makes sense. Thank you. I had another question from lecture 14. When at the beginning of the lecture, when you discussed like somebody doing a vertical jump and you said that the ground reaction force, like friction, would be pushing them forward, even though we were taught that friction is usually in the opposite direction.
That's a very common one that people so the question is, so if I have a person and there's gonna jump forward, right? The only forces that are acting in I've got gravity here. I've got a y component of the ground reaction force here, which is also the normal force, assuming I'm on flat ground. And I have a force here. And you're sitting there saying to, and I'm telling you that the only thing on that person, the only horizontal force acting on them that can at all accelerate them in this way is this guy. Remember, sum of forces equals mass times acceleration. So if we are going to accelerate in the x direction, we need a force in the x direction, and the only force that is acting in that x direction is this guy, is the frictional component of the ground reaction force, which means it has to be acting in this direction. Friction, however, let's just look at a shoe. I'm just looking at a shoe. Again, we all know by this point in time that I can't draw digitally at all. So we have our shoe, and I've got my ground reaction force and this is not a proper free body diagram because I'm not going to, because then I'd have to do what's happening at the ankle and stuff. But I just want to, basically, I'm doing a close-up of the shoe. If you look at friction here, which is this component right here, the X component of the ground reaction force, what I'm saying in terms of movement means imminent movement of the two surfaces with respect to each other, not with respect to the whole body. Okay, this part right here in the whole body, this tells us what is the direction the whole body is going to move, because I have a force in that direction. It's going to accelerate me in that direction. So that force has to be that way, and we know that force is being created by friction. However, if I look at the interaction between my shoe and the ground, if friction is acting this way, that means the foot is actually going to slide that way. Okay, that's what happens in friction. This is the amount of force I have that in the way opposite the two surfaces sliding. So picture doing a jump on ice. Okay, picture doing a jump on ice, because this is really where it comes. If you try and jump forward on ice, or even walk quickly forward on ice, yes, the friction has to be in this direction because it's trying to accelerate this way. But what happens to your foot? If you do that on ice, your foot slides backwards. So the actual motion between the shoe and the ground is in that the foot sliding backwards, even though that friction is used to provide you a force forward. Does that help?
Yes, it does. So when we're walking then, it would be the same, like the exact same thing as the shoe then, because our foot, like when we apply force with our foot on the ground, like I'm assuming at heel strike, like the foot is pushing back, so then friction is trying to accelerate you forward.
So when we have heel strike, and heel strike is there is a short period of time where the force does act the opposite direction. So you're right. At heel strike, there is a short period of time where friction acts in this direction, and you can tell that because when you heel strike walking fast on ice, what happens is your foot slides that way, right? So for a very short instant in time at heel strike, it actually decelerates your foot. Maybe not your whole body, because you have two forces at that point in time. You have one on one foot and one on the other foot. And the one on the one foot that's pushing is actually, which is your back foot at this point in time, is going to be greater than the one on your foot that's heel striking. And so for a very short period of time, when you heel strike, the force does act in that way on the shoe. And what would happen is your foot would slide forward. Again, your whole body would not necessarily do that, because you have your other foot behind you, which is doing this guy. And if the ground reaction force in the X direction on your back foot is bigger than the ground reaction force in the other direction on your front foot, you're still going to accelerate forward, but the actual foot itself might slide in this direction.
That makes sense. Thank you. I just had one last question.
Before you ask that, did somebody else have a question on this before I?
Yeah, I had a question on.
Yep.
Since the ground is the one putting the force upon our feet, just like you said, like it's not like what we're doing to the ground, but what the ground is doing to us.
Mm-hmm.
If the ground is applying a force that's moving backwards, would that be another explanation as to why our friction is moving forward, since the ground is exerting a force that's moving us backwards?
Well, the ground is putting a force that is acting forward on us. The ground is producing a force. if you, there's no question. The ground is pushing forward on us. We are pushing backwards on the ground. The ground is pushing forwards on us. It's at this time of the year. There's muddy patches out there. Well, there might be once it warms up again. If you find a muddy patch and walk quickly on it, what you'll find is you can see that the shoe pattern actually slipped backwards because it slipped backwards because the ground is pushing this way on us. And therefore we are pushing the other way on the ground. But the ground is definitely, for us to accelerate in this direction, if we want to accelerate in this direction, the ground has to act in that direction. Has to. Absolutely has to. So that's the ground pushing on us. We perceive the ground, what we do to the ground, but what happens to us is what the ground does to us.
So hence, if the ground is pushing us forward,
We
the
will.
friction would, the friction will be moving backwards to prevent us from slipping, right?
No, this is friction. This absolutely is friction. This force right here, this ground reaction force in the X direction, on level ground, let's be specific here about level ground. On level ground, the only force that we have that will accelerate us in the positive direction is, in the forward direction, is that ground reaction force. It's the only thing. And so the ground reaction force in the X direction is moving there. That's friction. That is friction. That is friction. So friction is moving, the force of friction is in that positive direction because it's accelerating us in that direction. It does mean that our foot would slide in the backwards direction, but our whole body is going to accelerate in the forward direction.
Oh, okay. So that's why I had the horizontal portion of the ground reaction force is friction.
Hmm?
The horizontal portion of the ground reaction force is friction.
Absolutely. On level ground, it is friction. This is friction. Absolutely. Okay, any other questions on this one? Leah, you had one more question?
Yeah, I just wanted to know, lecture 14, when we were talking about the resultant torque and you had the two graphs where you looked at like resultant joint torque and angular velocity, you said that when the graph was positive, the flexors would be the agonist. So my question is then, when the graph dips into the negative portion, would we consider then the hip extensors to be the agonist and then the flexors?
Yes. Now, that is from the textbook. Let me just see if I can find it. Whatever page it is in the textbook. That is definitely from the textbook. Without actually finding it right away, the point being that yes, and it depended if we were looking at I think there was different positives and negatives for the knees and the hips and the ankles. They weren't all flexors were positive, extensors were negative. I think on one of them it was extensors was positive and flexors was negative. But the point being that if the torque curve is, and it says on it, it's very clear on the graph whether positive is extensor or flexor. Let's say positive is extensor. If it's positive, that means the flexors are the agonist muscles, the flexors are the antagonist muscle, and you don't know if they're on. If it's negative, the flexors are the agonist muscle and the extensors are the antagonist muscle, and you do not know if those extensors are on. They can be completely off. Page 399. Thank you. Somebody put it in there for me.
So, sorry, I'm just a bit confused. So when the graph dips into the negative region then, so the extensors would be the agonist, right?
Okay, so if we're looking at the graphs on 399, which are the ones that I explained in that lecture, and we are looking first at the hips where the flexors are positive and the extensors are negative. In that graph, when the torque curve, which is the resultant joint torque, dips down into the negatives, then that means the extensors are the agonist muscle, period. That's all there is to it. If the extensors are, if the torque curve is negative, if the resultant joint torque is negative, that means the extensors in that curve are the agonist muscle.
So Professor, I have a question.
Yep.
Best of that, if I start my analysis and I define my flexors as the negatives and the extensors as the positive,
Mm-hmm.
I do the resultant talk, I get a negative answer. Whatever I defined as negative would be my agonist, right?
Yes, exactly. Got it.
Okay.
And that's why I said in the joint torque point of that when we were talking about free body diagrams and which direction you put the joint forces and the torque, that is up to the person, but you put it in the free body diagram so you're communicating to anybody who's looking at your work what you considered positive and what you considered negative.
Okay.
And you can see here in these graphs that there were different ones that were considered positive and negative, depending on whether you were looking at the hip, the knee, or the ankle. So
I have a question.
on this,
So, yeah, on this. So I thought it was that when it was positive, it was the agonist, and when it was negative, it was the antagonist.
no.
No?
When it's positive, it's for example, on the first one, when it's positive, it's the flexors that are the agonist, and this is for the hip. And when it's negative, the extensors are the agonist.
Okay. So whenever it crosses 0, it changes which one is the agonist.
Absolutely. Yes.
Okay.
You got it. That's it.
Okay, thank you.
So
And
it's just about
You're
it's just
walking.
about-
Sorry?
so it's just about what we define it as, right?
Yes.
So I mean how we get the agonist. Okay.
It's basically how you drew your free body diagram and then therefore how you put it into your equations, whether you put it into your equation as a positive or a negative. So, yep, that's it. Any other questions on that one?
Yeah, on the slides, page 34, you said that anytime the joint torque curve crosses into the positive area, the positive muscles must be the agonist. So,
The positive muscles are the agonist, yes. And when it goes down into the negatives, the negative muscles are the agonist.
but the start doesn't matter, right?
At any instant in time. So let's say I look at 25%, if you're looking at those curves on page 399, and I'm looking at 25% of swing time, and I'm looking at the hip. And at that instant in time, the joint torque, the resultant joint torque curve is positive. At that instant in time, at 25% of swing, that means my flexors are my agonist muscle. If I look at 75% of swing time, my resultant joint torque curve is negative, which means that my extensors are my agonist muscle at that instant in time.
So if we changed it, so then if we said that flexion was positive and extension would be negative, then it would invert the graph, right?
Yep, it would.
And
Exactly.
it would still work because you define the extensors would be negative and it will still be the agonist.
Yep.
Okay. All right. Thank you.
Any other questions on this? Okay. Eli.
Hi, Dr. Moore. I have several conceptual questions, but they're relatively quick. So just in case if it takes a lot of time, then I'll let other people go. I just have a lab coming up, but they're really quick. So for chapter 6, additional problem 7, I know you went over it in a previous tutorial about calculating the cross-sectional area of a muscle.
Yeah, and I did at one point actually make a mistake, and I apologize if you went through that. You'll have noted that if you were listening to it initially, the answer that is given is correct. Yeah.
I was just wondering for like which one we have to use. Do we have to use the force developed by the tendon or the force developed by the muscle? Because for part, in order to get the right answer, for one of them you had to use F tendon in part A, and you had to use F muscle in part B. So how are we supposed to know?
No, you don't. No, you don't. If you get 1.7 centimeters, you're using the, it's always the fibers. It's always the fibers. Always the fibers. And so in the first one, you are basically have the muscle fibers is 150. So if you divide 150 by 90, I think you're going to get the 1.7, right?
I guess. Let me just get out my.
So 150 divided by 90.
Oh wait, 1.7.
1.7.
Yeah, 1.7 centimeters squared. In the second one, how much force must be produced by the fibers of a pennate muscle? The answer is 400. So again, 400 is fibers. In this question, those two questions are reversed, right? So you're taking that 400 newtons in this one and dividing it by 90, which gives you the 4.4 centimeters squared. So in both cases, you are using the fibers. Both cases, you are using the fibers.
Got it. So my next question was regarding the fusiform arrangement. So the force developed by the tendon is equal to the force developed by the muscle.
The force divided by the
developed by the tendon is equal to the force of the muscle.
What aspect of the muscle?
I'm not entirely sure, but I would just think technically angle of pennation would be 0, so you'd have cos of 0, which is 1.
Oh yeah, so in a parallel muscle. So you're talking parallel. In a parallel, yes. In a parallel, the muscle, the force produced by the fibers is the force that goes straight down your tendon. That's right. There's no penalty in a parallel fiber arrangement, which is the advantage of the parallel fiber arrangement. The disadvantage is that you can't put as many fibers, you can't get as big a cross-sectional area.
And one other question I had is if the agonist muscle is doing a concentric contraction,
That
Mhm.
means the antagonist will either be off or doing an eccentric contraction.
Yep.
Okay.
But you don't know if it's on or off. But you're right. If it happens to be on, if you do co-contract and your agonist, meaning the muscle, the muscles that you need to have on, are concentrically contracting, then the antagonist would be eccentrically contracting. Yes.
Perfect. And my last
Or
question
vice
was,
versa.
and so my last question was, for the upcoming midterm, when, in terms of how much anatomy knowledge we need to have, like, what do you suggest we go over for things like active passive insufficiency and for agonists doing eccentric contraction? So what should we focus on? Like, do we need to know which muscles are going to be doing an eccentric contraction in a particular movement? What do you suggest we go over?
Well, first of all, you didn't in anatomy figure out which muscle was eccentric and which one was concentric in a particular movement, because that part of it is kind of biomechanics. And I would have to give you the information on the velocity and the torque. So you need to know which muscle is the agonist, and which direction the joint is moving, in order to figure out whether the agonist muscle is acting eccentrically or concentrically. And that was that graph on 399 that we just went over. So you need to know that. You need to be able to interpret that type of graph. If they're going in the same direction, so if it's shortening at the same time, if it's flexing at the same time the flexors are the agonist muscle, it's a concentric contraction. If it's extending at the same time that the flexors are the agonist muscle, then it's an eccentric contraction.
Got it. Thank you so much.
No problem. That it? Okay. Blaze.
Yeah. Okay. So my question is on chapter 10, extra practice problem 8. It's the one on, like, a ball is kicked a horizontal distance if it reaches a maximum height. Was it kicked at greater or less than or equal to 45 degrees? And the answer says it's greater than, but I can't figure out why.
Well, I'm not going to take the time to do that problem. You can go back to the tutorials we did just before the first midterm, because we did do that question.
Okay.
But basically, and it's a projectile analysis question, and I'm not going to have people do the math of a projectile analysis for this midterm. That being said, it's just that you have to figure out that chapter 10, did you say?
Yeah, chapter 10.
You have to figure out how far it would have gone. You basically have to figure out the two velocities. You have to figure out the horizontal and the vertical components of the takeoff velocities.
Okay.
And if they are the same, there's 45 degrees. If the horizontal is bigger than the vertical, it's less than 45 degrees. If the vertical is bigger, if the horizontal is bigger than the vertical, it's less than 45 degrees. If the vertical is bigger than the horizontal, it's greater than 45 degrees.
Okay, thank you.
You're welcome. Is that the only one?
Yeah.
Okay, Brenda.
My question was basically answered. It was about the results and stuff. I didn't put my hand down. I had the same question too.
Okay, so you're good. Kate.
Hi, I was just wondering how many questions are going to be on the midterm and how long are we getting?
I will post it. It'll be 45 minutes again, same as before. I will post tomorrow morning the exact numbers. It will be again a scenario where some of the questions are worth more than one, so that I will try to take it down a notch in terms of the number of parts of a question. Fair enough?
Okay, thank you.
Okay, Elena.
Hi, good morning. Could you go through the chapter 13, introductory problem 6?
13, additional problem 6.
No, introductory.
Oh, introductory problem 6. Thank you. Sorry, Elena. To which lever classes do a golf club, a swinging door, and a broom belong? So in a lot of those, it sort of depends on how you picture it and how you do it, to be honest. So let's start with the broom. If I broom, say I have a broom, the force is, there's going to be some force here, which is your resistance force, your load.
Mm-hmm. Mm-hmm.
And then you can sweep in two ways. One where you hold this one kind of with one hand and then do the sweeping action with that hand.
Mm-hmm. Oh, this is third class, right?
Yes, exactly. Or you can actually, I think this that's the more efficient way of sweeping. To be honest, I think it's kind of a combination of both of the two that I'm going to show you. You can put the force here, here, and hold it as a fulcrum with that hand, right? You could do both. It's how you choose to sweep. I think a lot of people do this, where you actually have two forces that both forces move.
Mm-hmm.
But so I would take either, as long as you drew the free body diagram in an appropriate way and understood what was happening. You held it at the top and you swept with the other. That's your third class. The golf club.
Yeah, I was stuck with that one.
Why is the golf club even a lever? It's moving. The reality is the golf club is really your arm plus the golf club. And you are pivoting around, let's say, your shoulder. And I wouldn't ask you this one, kind of, because again, so if I've got my arm.
So it looks like the same force and fulcrum. It's the same place.
So you're coming down there. Your force is here, right? Once it hits the ground.
Resistance, right?
Your resistance force is going to be there. And in this particular case, I would say that the actual force is the muscle force at the shoulder, which is pulling you down this way. That's, to me, what's actually happening, because the problem with even if you looked at it from the hand perspective, I suppose you could say that if you got rid of this, that there's sort of a rotation at your wrist, and that you are still probably, sorry, again, it's probably there, and there. So as you rotate around with your wrists, you're holding it at the top, and then you're rotating it around, which is, again, as far as I'm concerned, when you're doing your golf swing, you really, it's a whole arm plus golf club scenario.
But yeah, but still the force you applied force in the middle.
Yeah, you would apply, in that kind of case, you are sort of having the head of the, you're doing both within your hand. In one end of your hand, you're holding it straight, and with the other side of your hand, probably with your other hand, you are rotating it like that.
Okay.
Swinging door.
Yeah, this is the second class, so it's.
Yeah, exactly. You got it.
Yeah, so this is easy. This one is easy. I was back with golf club. Thank you.
You're welcome. That's it?
Yeah.
Okay. Conchetta?
Hi, yeah. I just have two questions. So the first is regarding the advantage of a third class lever. So it's the speed and the range of motion. And is that because the moment arm between the axes of rotation and the resistance is the longest?
Well, let's just think about it. If we go back to if we go back to radial, well, just switching from angular velocity to an angular distance to linear distance, just think about those scenarios. So if I have let's go with the forearm in hand again. Forearm in hand where, my load is here and my muscle is attaching here and my axis of rotation is there. As my arm goes up, so if I'm going to rotate my arm, that's going to go around there, and this is going to go around here, right? Does that make sense?
Yeah.
So I hope you can see that in doing that, the distance traveled by the insertion of the biceps is a lot smaller than the distance traveled by by your hand itself. You only have so much distance that you can move within your muscle, right? If your muscle was attached way out here, it would have to shorten substantially in order for you to do the full range of motion. Here it has to shorten, but it doesn't have to shorten as much. So if you think about it in terms of when let's say I travel from here to here, all of the parts of my arm are going to move that same over the same time. because they're all going through that same angle at the same time. But this guy right here does not have to travel anywhere near the distance that this guy out here does. So this one has a lot of advantages in terms of velocity, because it just doesn't have to move as far in that same distance and time.
Yeah, that makes sense.
Okay, good. Because that's the advantage. I mean, it just, you don't have to travel as far, so you can do it.
Right.
If it had to do there, it would just be, wow.
Yeah, perfect. Thank you. Also, I just had a question from chapter 13,
Yeah.
additional problem number 6.
Additional problem number 6. Oh, the picking up the suitcase?
Yeah.
Okay, well, we've done this one before, but I'll just very quickly go over it again. I have a few minutes still. Again, drawing, not my strength. So, person standing there, center of gravity's in the center. And we're only looking at left to right. We aren't looking up to down. We are only looking left to right. And they happen to be at it's a 600 Newton person, 600 Newtons. And they're picking up a suitcase. And the suitcase, which is going to end up being here, is, and they don't lean over at all, so that 600 Newtons still stays in the center of this person. And this is a 180 Newton suitcase. And the distance from there to there is 20 centimeters. So to get the x c of g, we get the sum of the masses times x of I just means the different parts. In this case, there's 2. There's the person and the suitcase. And this just fancy symbol for sum of, and this is the sum of the mass. Well, the sum of the mass is the 2 added together, so now, you could be tricked here, because what I'm showing here is not a mass, is it? It's a weight. This equation right here works the same whether you use mass, whether you use weight, or whether you use mass fraction. So this is, a fraction of the total body. This is a fraction of the total body, which we use in body segments. As long as you use the same one all the way through, because of course, yeah, I would be dividing this by 9.81. Well, if I divide this by 9.81 and I divide this by 9.81, that actually cancels. So again, whether you use mass or whether you use weight or whether you use mass fraction, it will work the same. Just be consistent and use the same all the way through. The sum of the masses times the x's, and again, I'm going to use weight, not mass, and I recognize that is going to be 600 times, what is my x value? Well, I have to decide where my origin is. If I make my origin right here, because that's where it asks you to do it from. So how much does it move from there? So this is 0, and this is 20, right? So 600 times 0 plus 180 times 20. So, which I believe is 3,600. And this will be Newton centimeters. So if I go back to this, it's 3,600 Newton centimeters divided by 780 newtons. The newtons will cancel. I'll be left with centimeters, and that is your 4.6, I believe it is, centimeters. And you're shifting this way 4.6 centimeters. Now, does that make sense? Yes, it's between the center of the person, or the center of gravity of the person, and the suitcase. If it was, 25 centimeters, we would know we've done it wrong because it would be outside both of them. And it should be closer to the heavier one. Well, the person weighs 600 newtons and the suitcase is only 180 newtons. So it's closer to the person.
Okay,
Any
yeah, that
questions?
makes sense. Yeah, thank you.
You're welcome. Any questions on that one, anybody? Okay. Amos.
Yeah, I just want to make sure my understanding is correct with the force velocity curve. So what I imagine is that with the concentric, the reason why we cannot generate as much force when it's like a fast shortening velocity is because we have less time for the cross bridges to form. And then for the eccentric, it's faster with a like a faster rate of lengthening velocity, because you increase the amount of energy that's absorbed by like the elastic components to recoil. Is that correct?
So basically, it does come down to cross bridges, and they have to cycle, and they have to release and go and grab and pull and grab and pull. So yes, you've got two things happening there. You have that you aren't going to have as many cross bridges, because as they have to release and pull and release and pull, they just can't be attached as long. The other thing you have is that if you're swimming with the fluid, like against the fluid, they actually have to take some of that force just to move to get to the next cross bridge. Because you think about it, the inside of a muscle fiber, most people don't think about, how much force does it actually take just to move the proteins, the actin and myosin, with respect to each other. When you're going the other way, it's going with the same direction of the force, so it helps you. The fact that you have this resistance from the fluids around you, it actually increases the force. So that's one reason. And the other way, you can actually get a cross bridge. You're right, it gets stretched. It can hold on longer and get stretched, and then it'll swing back into place and then get stretched and then swing. So yes, you get the added force coming from the series elastic component. Series elastic component. All good?
Yeah, there's just one more. I'm pretty sure this is already answered, but it's about the angle of attachment, because that is different from joint angle, where it's kind of like opposite, if that makes sense. So if the angle of attachment is greater than 90 degrees, your joint angle is actually less than 90 degrees. Does that make sense?
Well, in the biceps, that's true. Like, yeah, yeah. In the biceps, it's certainly true. In a certain respect, they're a little. They're not independent. They're not independent, but they're joint specific.
Do you have like an example where that might not be the same thing?
Well, in something like the patellar tendon, right? Which is, essentially quadriceps coming in. There's no point where it's actually 90 degrees.
Okay, so then how would you describe it? And if there's no 90 degrees, then what would be the like optimal how you say it, the optimal rotary component for that tendon?
It's specific to the muscle and the tendon. Like, you'd have to look at it. I mean, the optimal rotary component is always going to be if it can come in at 90 degrees. The reality is that a lot of moment arms just happens to be how far away that muscle is and from the joint. You guys get the simplicity. Let's face it, the biceps is the easiest one to picture all of this. In a lot of cases, what we would do is we would move a person through, in let's say an MRI, through a range of motion, and while we put them through the range of motion, we would take the we would be able to find the joint center, and we would able to at each point in time or each posture, and we would look at the tendons that are crossing that joint to find out, literally create the path so we could figure out where the moment arm is, which is, we would take that, figure out what that path is. We would take 90 degrees from that path in such a way that it would cross the joint center, and we would measure that distance, and we would get the moment arms directly, as opposed to taking the distance of attachment. A lot of muscles don't attach totally at one, some attach along a bone, right? So you need to be able to track the tendon as it crosses the joint in order to find out what that moment arm is. Fair enough?
Yeah, thank you.
Any other questions, Amos?
Maybe if no one else has some, but I'd rather wait for them right now.
Elena, did you have another question?
Yeah, I have a question about lap 8 actually. So we did center of gravity, like a person, counted center of gravity of a person, right?
Yeah.
But it holds in some weight. So in that case, so weight is not a part of system.
Well, it depends what you are choosing to do, be part of the system. So the person picking up the suitcase, as we just did in question 6.
Yeah, in that case, it was part of system.
Yes. So it just depends on what you are defining as the system in that particular case.
Mm-hmm. But in the lab, so it holds something, but it has weight.
Yeah, in the lab, you are actually finding the person, not the weight. You're right, not the weight in the lab one, because the idea is that's the approach we would take if we were analyzing what's happening at somebody's back. Mm-hmm. and we would separate out what's in their hands and what the upper body is doing.
Mhm.
And that's typically how we do that. Yeah.
Because how should we? What's the approach in that case? What cases we think it's a part of the system, and in some cases it's not. So how to separate it? How to
Well,
approach?
for this,
For example, in your lecture you told, so when you hold a pie in front of you, so it could be part of the system, it could be not. So
so
it affects.
it depends on what your question is. If your question is, where would how would the center of gravity of the person move with the pie? Because we haven't got there yet, but for balance, your center of gravity, the X has to be
should shift, right?
It has to be within your base of support or you'll fall over. So in that type of question, then what you have in your hand is important, because if I'm holding something really heavy out here, I'm much more likely to fall over. So in that type of question, it would be of the whole system. In question that you did in the lab, which is very typical to if you were working with the risk of low back injury in a workplace, we tend to keep them separate so that we can always be adjusting what we have on our hands and what posture we're in, because what posture you're in makes a difference, and what you have in your hand makes a difference. And in that case, if you're in a posture where it's already bad for your low back, adding any weight in your hands is going to be bad. So if you start with what the body's doing, and then you can look at what you can add into the hands without creating a risk.
I see.
Yeah.
Thank you.
I have time for one more quick question. Aaliyah, did you have another?
Yeah, just a quick question. So about the format, it's going to be the same as last time, like multiple choice, fill in the blank?
Fill in the blank, matching. The only difference will be there will be somewhere you might actually have to write a little what's happening here scenario that we will mark. You don't have to you can type it right in, but you won't. What would you expect to happen in this situation, kind of thing.
Okay, got it. Thank you.
Okay. Good. Well, with that, I have to move to my next meeting. So turn off the recording.